Welcome in. Thank you for joining. Nice to have you here today. Get ready. Grab a notebook, a pen, or a pencil. Whichever thing you choose to write with is fine. This is math from the void. Math coming at you from out of nowhere. We got some pretty peaceful pitter-patter of rain outside too, which I don't know if you can hear that over the void, but adds to the ambiance. Okay, anyways, today we have a nice problem from the 2000 AP Calculus exam. This was on the AB and the BC exam, so if you're in AB, you can totally handle this. I do just want to indicate that these are straight line segments with the points 3, 10, and then we have a flat line segment that this goes up to 10, 10. The sort of x-axis is time, this is t, and this is velocity of someone named runner A, so we'll call it VA. Yeah. All right, so given that, go ahead and give the problem a look-see. See what you think. You should give yourself about, 12 to 15 minutes. And then when you're ready, you can come back and join. Because here we go. So we have two runners, A and B. We've already met A on a straight racetrack for 0 to 10 seconds. The graph here consists of two line segments, is showing the velocity in meters per second of runner A. So this is specifically runner A. Whereas runner B's velocity, for some reason, is defined by this equation. Find the velocity of runner A and the velocity of runner B at time t equals 2 seconds. So this is pretty easy because the velocity is just right here on the graph for us. Now, if it's sort of hard to see, you can use the fact that this straight line segment goes up to 3, 10. So the slope is 10 over 3. Okay. So that means 1 second in, we're going to be at 10 thirds. And then 2 seconds in, we're going to be at 20 thirds. Right? And then finally, we're going to be at 30 thirds, which is also just known as 10. So if you realize that the slope of that line is 10 thirds, it's pretty easy to figure that the velocity of runner A at 2 seconds is 20 thirds, and this is in meters per second. Whereas the velocity of runner B after 2 seconds, well, we just have to plug in 2 to this function here. I have a feeling I'm going to want to divide with long division, divide this function, but we'll see. That's yet to be determined. If I plug in a 2, we're just going to get 48 over 2 times 2 is 4, plus 3 is 7. So 48 over 7 meters per second. I don't think they need you to simplify that. I'm sure that's fine, even though I believe this is a calculator problem because of the type of function they're giving us, but we'll see. So this is our answer for part A. Very easy. Very, very easy. Find the acceleration of runner A and the acceleration of runner B at time t equals 2. So the acceleration is the slope of the velocity. It's the derivative of the velocity. So that's just going to be the slope of this line segment for runner A. So that's going to be exactly 10 thirds. So the acceleration of runner A at 2 seconds is simply 10 thirds. That's pretty easy to figure out. I guess finding the acceleration of runner B would be a little bit tougher, so let's do this. We'll say A of B with of t, the acceleration of runner B as a function of time is going to be the derivative. So we have a quotient. So however you remember the quotient rule is fine. I know it as HODI high, so 2t plus 3 times the derivative of the top, 24, minus the top, 24t, d ho, derivative of the bottom, all over the ho-ho, 2t plus 3 squared. So if I want to plug in 2, I don't really need to simplify all of that. I can just plug 2 in directly. Should be fine. So we're going to have 2 times 2 is 4 plus 3 is 7 times 24 minus 24 times 2 times 2. That's 4 times 24. So I'm going to make my life easier by thinking of it like that. And then this is over 2 times 2 plus 3 is 7 squared. So this is going to be 3 times 24 over 49. I can call that 72 over 49. Oh, and I forgot to indicate units. This is going to be in meters per second squared. And if they really need you to divide that, how precise can we get here? Okay, we have 149. This is 23. 230 doesn't make it 5 times, but it does make it 4 times. That's going to be 196, leaving us with 34, so 340. And that goes in about 7 times. So that's going to give us, oh, maybe not 7 times. 6 times, sorry. Just barely. Let's see, so that's going to give us 294, leaving us with 46 here. And so that's going to give us a 9. So I think if you wanted to call it 1.47 meters per second squared, that's probably fine. And for this other dude, it's very clearly 10 thirds, or if you want to call it, 3.3 repeated, that's fine as well. Meters per second squared. Okay. Yeah, so it says indicate units of measure. That means you really need to put those units, otherwise you can probably lose a point on each of those, which would suck. Find the total distance run by runner A and the total distance run. So total distance, that's going to be using the integral. So part B had us use the derivative of the velocity, that's the acceleration. Now we're finding total distance, which is the integral of technically of the absolute value of the velocity, but it doesn't seem like their velocities are ever going to be negative, so we don't really have to worry about that. Again, runner A is sort of the easy one to tabulate. You can see that runner A's velocity increased steadily, and then he just kept booking it. He didn't pick up his speed at the end there. I think he probably should have maybe had a better last kick or last push. I don't know. Who am I to talk? I'm not a runner. So, the total distance for A, we'll just call it D, I guess. dA is simply going to be the integral. Oh, this is from 0 to 10? Yeah, from 0 to 10. So the integral from 0 to 10 of VA dt, which is just going to basically be adding up the area of this very simple trapezoid here. Okay. We're not going to use like an antiderivative. We're just going to use the trapezoid. You could break this into 2 functions and then do it piecewise, but there's no need to do that. Just find the area of this shape. Or you can break it into a triangle and a rectangle. I know a lot of kids are doing that these days because you're not comfortable with like the basic trapezoid formula for some reason. So the base is 10, the other base is 7 over 2 times the height, which is 10. Okay, pretty clear. So this is going to be 75. Is it? Is it 85? It's 85. Sorry, guys. There we go. And this is going to be in meters, I guess. It's pretty good. I was going to say 10 seconds to run the 100-meter dash. That would be Usain Bolt level. This is 85 meters, so still really fast, I think. Way faster than me. Let's find the distance for this person. Yes. Not going to be the easiest thing there. So what I'm going to do, because I'm doing this by hand, you could just plug it into a calculator, I'm sure, but I don't know. Maybe they do want you to divide this. So if we divide this, 24t divided by 2t plus 3, that's going to give us, and we'll call this plus 0, that's going to give us 12, which leaves us with 24t, 36. We subtract those. Negative 36. And so that's our remainder. So our function v for runner B really is the same thing as 12 minus 36 over 2t plus 3. Yeah, I think that's perfectly doable as far as integral goes. We'll get an expression with ln, but that's okay. So dB, I guess of 10 is really what we're getting. So back there I should have put, I just put dA. So yeah, that works. dB of 10 is equal to the integral from 0 to 10 of 12 minus 36 over 2t plus 3 dt. Well, that's just going to be 12t minus 18 ln of, I don't have to put absolute value because these t values are never going to cause it to be negative inside. And that's going to go from 0 to 10. Okay. So let's plug that in. We're going to get 120 minus 18 ln of 23. That's pretty funny. No idea what that is. Minus, well, 12 times 0 is just 0. Minus 18 ln of 0 plus 3. Well, that's just 3. Okay, so this is 120 plus 18 ln of 3 minus 18 ln of 23. This is interesting. So this is going to be 120 plus ln of, I guess I'll say 18 ln of 3 over 23. Starting to lose the significance of this here. But yeah, apparently that's what it comes out to be. So these are likely very, very small numbers. That'll be my distance. I might not get full credit for that if I were to put that on the exam, but I mean, that is the calculation. So yeah, let's see. Did I subtract that correctly? 36, you subtract it, yeah. And then you take an integral. Yeah, I mean, you can see it for yourself that that's going to be the derivative, right? If you take a derivative of this, you're going to have 18 times 1 over 2t plus 3, but then times 2. So yeah, 36. All right. I think I might have done a little extra by dividing this and doing the long division, but it's good to keep your pre-calculus skills, handy. You need to use them constantly on the exam, so you really need to focus on more of the concepts than just remembering specific formulas and rules. Anyway, that's enough blab out of me. I'll see you next time.